Hello, and welcome to another rousing episode of AP Stats with Mr. Joe. Today, we are talking about when we reject or not reject a hypothesis. Yesterday, we talked about the difference between a null hypothesis and an alternative hypothesis, and we know that we either reject the null hypothesis or do not reject the whole null hypothesis. So, when do we actually know when to actually reject it? Well, let's go look at. We use a thing called hypothesis testing. What is hypothesis testing and what is our goal? Well, really, our goal is to answer the question: how likely is it to get a result similar to our alternative hypothesis just by chance when the null hypothesis is true? So we're going to sort of work through an example and see what that looks like. Mr. Cho is wondering what Lin Camp thinks about its football team. Another teacher states that they're 99% sure that 50% of the student body enjoys watching our Wildcats play. Mr. Cho thinks otherwise. He thinks less than 50% of students enjoy watching the Wildcats. So, in this case, our null hypothesis is 0.5 because, well, that's the status quo. That's what we think is currently the actual support for Lin Camps is. But Mr. Cho thinks otherwise. He thinks it's less than 0.5. So our alternative hypothesis is P is less than 0.5. Remember, our proportion is the proportion of students who enjoy watching Wildcats play. So our goal in this case is to determine if Mr. Cho took a sample of 50 students, what's the likelihood of finding that proportion to be less than 50%? So let's say Mr. Cho does his sample, and when he did his sample, he found only 12 students actually enjoy watching the Wildcats out of 50. So another teacher said it should have been 50%. So we really should have gotten 25 out of 50 students. So really, if Mr. Cho got 12 out of 50, there are two possibilities for this. It was A, completely random, like he just randomly, it was just really bad luck for Mr. Cho to find 12 students. Or the null hypothesis is wrong. So 50% of the students don't actually like the Wildcats. So it's either those two options. It's either completely by chance or its null hypothesis is just wrong. So how do we determine between the two? How do we know if it's completely by chance or if the null hypothesis is wrong? So that's when we come up with a p-value. The p-value in this case is the probability that the statistic would take a value as extreme or more extreme than the one we actually observed. So the p-value in this case is how likely Mr. Cho would find only 12 or even less than 12 students who enjoy the Wildcats. And that is what our p-value is. It's that probability that that statistic would be that number. And so now a little bit more on p-value. The lower the p-value, the more likely an observation would happen, which makes sense. If your probability is lower, the less of a chance that would actually happen. So how do we know what makes our p-value low enough to know that it's not due to random chance? Well, it needs to be quote unquote statistically significant before it's considered low enough. So what does it mean to be statistically significant? Well, in the normal world, we say significant equals important. Like significant other, significant digits, great significant. When you do something of great significance, that means you did something really important. In the stats world, significant means something completely different. It means not likely to happen just by chance. So then we know our p-value is not due to chance if it's statistically significant. But what makes something statistically significant? Well, we take our p-value and we compare it to a thing called alpha level. In this case, it's a Greek letter alpha, but my PowerPoint slide won't let me type out alpha. You see a picture of alpha right here. But we compare our p-value to our alpha level, and if it's less than our alpha level, then it is considered statistically significant. So what is an alpha level? Well, an alpha level is sort of like a boundary we set. We can usually you'll see an alpha level of 0.05. So basically, we are saying that we consider data significant enough if what we get happens less than 5% of the time, if our null hypothesis is true. And so this is sort of like a level that anybody can really set. A lot of times, uh, companies use a 0.05, but also a lot of times companies also use a zero point 0.1 alpha level. So if something happens less than 10% of the time, they consider it statistically significant. So will it always be 0.05? No. A lot of AP Stat questions will have an alpha level of 0.01 or 0.1. But if they don't say anything about that, you can set your own alpha level to be 0.05. That's just basically the go-to alpha level for the most part. When I took AP Stats, that's the sort of alpha level I hit every single time. So let's go back to Mr. Cho. Let's say he found that, so we looked at, remember, 12 out of 50 students liking a Wildcat. So what's the probability of that happening? So we calculate the probability using a crazy test statistic that we will talk about later. And he found that it only happens 0.000118 of the time. So basically that is 0.01% of the time. And so because our p-value is less than our alpha, which is again 0.05, we can reject the null hypothesis. If it was higher than 5%, we do not reject that null hypothesis. But in this case, we do. So that just sort of remember that. If it's lower than the alpha, we reject the hoe. If it's greater than the alpha, we do not reject the hoe. Never accept the hoe, though. So let's do a couple of examples. Back to Mr. Cho. He is a basketball all-star. He makes 80% of his free throws. But like one time, a student saw him making only 36% defeat 36 out of 50 free throws. So then who's lying? Like if Mr. Cho really makes 80% of his free throws, he shouldn't be making less than 40, right? So our null hypothesis is going to be 0.08, 0.8, excuse me. And before, like what's our null hypothesis or what's our alternative hypothesis? So we're looking at him making less than 80%. So pause the video, think of what the alternative video is, and then unpause. Right. So our null alternative hypothesis should be less than p. It should be p less than 0.8. And then Mr. Cho, took out his calculator and was like, "No, random student child, you're completely wrong." So he conducted a significance test, which resulted in a p-value of 0.07865. So that means if he did shoot his free throws 80% of the time, there is only a 7.865% chance of him making either 36 free throws at once or less than 36 free throws at once. Mr. Cho has his p-value now. So now let's take that p-value and compare it to a couple of alpha levels. So first we're going to look at an alpha level of 0.10. And so because the p-value is less than alpha equals 0.10, we can reject the hoe. We do have convincing evidence that Mr. Cho does not make 80% of the free throws that he takes. But if we look at it with an alpha level of 0.05, because a p-value of 0.07 is greater than the alpha of 0.05, we do not reject the HO. We do not have convincing evidence that Mr. Cho does not make 80% of the free throws that he takes. So, if you need another example, you can keep on clicking, but if you feel pretty good about, when to reject the HO and when to not reject the HO, feel free to stop the video now. So example 2. Simon reads a newspaper report claiming that 12% of all students in the U.S. are left-handed. Simon chooses an SRS of 100 students and finds that 16 are left-handed. A significance test yields a p-value of 0.2184. What conclusion can you make for alpha equals 0.1 Well, what if the alpha equals 0.05? Justify your answer. So, our null and alternative hypothesis is going to be p equals 0.12 and p does not equal 0.12, where p is going to be the proportion of college students who are left-handed. So, think about the answers. Think about, well, is my p-value less than or greater than our alpha level? And so for the both of them, actually, both times the p-value is greater than the alpha level of 0.10 and the alpha level of 0.05, we can say both times we do not have convincing evidence that the proportion of left-handed students at Sinus College is different from the national proportion. So because, again, for p-value for both of these, and they're both greater than 0.1, remember our p-value is 0.2184, and because it's greater than 0.10 and 0.005, we do not have convincing evidence. So that's it. It's pretty cool. And then next time you'll see me, we're gonna get into type 1 and type 2 errors. Well, what does that mean, Mr. Cho? Well, we'll find out. I'll see you later. See ya. Deuces.